Now we will discuss about the well-posedness of Cauchy problem for the one-dimensional wave equation. Okay. Uh, it is stated as the theorem 4.4, that is fix capital T greater than 0. The Cauchy problem, uh, utt minus c square into uxx equal to 0. The homogeneous Cauchy problem for the one-dimensional wave equation, that is uxx equal to 0, where minus infinity less than x less than infinity, t greater than 0. With respect to the initial conditions, u at x0 is equal to f of x and ut at x0 is equal to g of x for minus infinity less than x less than infinity. The Cauchy problem is given by like this. Then the theorem says that the Cauchy problem uh, in the domain minus infinity less than x less than infinity and 0 less than or equal to small t less than or equal to capital T is well paused for f belong to C2 of R and G belong to C1 of R. Okay. So the statement of the theorem is, or the theorem says that the Cauchy problem for the one-dimensional wave equation, that is given by utt minus u c square uxx equal to 0 for minus infinity less than x less than infinity and t greater than 0 with the initial conditions u at x0 equal to fx and ut at x0 equal to g of x. This Cauchy problem will be well paused in the domain minus infinity less than x less than infinity and 0 less than or equal to t less than or equal to capital T for f belong to C2R and g belong to C1 of R. So we need to show that the Cauchy problem is well paused in this domain, in this particular domain, that is minus infinity to infinity. X is in minus infinity to infinity and t belong to closed interval 0 capital T. So for this domain, the Cauchy problem is well paused. And we know that a problem is said to be well paused if it has the Hadamard conditions for the well pausedness. That means it has a solution and it has a unique solution, and the next thing is the solution must be stable. That means with respect to small changes in the initial conditions, there will be small changes in the solution also. And this may not give rise to a large and extreme change in the solutions. Okay. So this we need to show. And in the last lectures, we have already proved or we have already shown that the Cauchy problem has a unique, has a solution that is given by the D'Alembert's formula, and that solution is unique also. So the existence and uniqueness part of well-posedness follows directly from the D'Alembert's formula. That is the existence and uniqueness of solutions follow directly from the D'Alembert's formula. And indeed, this formula provides us with a solution, and we have shown that any solution of the Cauchy problem is necessarily equal to the D'Alembert solution. And we have already shown that any solution of the Cauchy problem is necessarily equal to the D'Alembert solution. Is necessarily equal to the D'Alembert's solution. Okay. Also, the solution that is U is classical since we have our assumption. Since from our assumption, from our smoothness assumption, that means uh, assumption that is F belong to C2 of R and G belong to C1 of R, that we have already assumed. Then it follows that from this assumption it follows that the solution U belong to C2 of R cross 0 infinity, open interval 0 infinity, intersection C1 of R cross closed 0 infinity. Okay, so the solution is a classical solution. Solution is a classical solution. Okay, and on the other hand, if F belong to C of R, if F belong to C of R and G is locally integrable and G is locally integrable, then the D'Alembert solution is a generalized solution. Then the D'Alembert solution is a generalized solution. Okay. So we have proved the existence and uniqueness of the Cauchy problem by the D'Alembert solution. Okay. Now it remains only to show that the Cauchy problem is stable, or it remains to show that it remains to prove the stability of the Cauchy problem. The third condition for the well-posedness, the stability of the Cauchy problem. That means we need to show that for a small change in the initial condition, it gives rise to only a small change in the solution. Or that is, we need to show that small changes in the initial conditions give rise to small change in the solution. So now we need to show this one. And for that, let ui, that is u1, u2, be the two solutions of the Cauchy problem with the initial conditions fi and gi for where I equal to 1, 2, 3. Or let u1 be the solution of the Cauchy problem, or let u1 be the solution of the Cauchy problem. 1, let me may denote it as 1, the Cauchy problem with the initial conditions f1 and g1, and u2 be the solution of the Cauchy problem 1 with f2 and g2 as initial conditions. Okay. So U1 is the corresponding solution of the Cauchy problem for the Cauchy problem with the initial conditions F1 and Fg1, and U2 be the solution of the Cauchy problem with the F2 and G2 as the initial conditions. That means U of at x0 is equal to F2 and UT at x0 equal to G2 for the solution, and its solution may be the is calculated as U2. Okay, then we need to show that uh, now if there is a change in the initial conditions, that is if f1 of x minus f2 of x is less than delta and and the two initial conditions, and mod g1 of x minus g2 of x is also less than delta for all x belongs to R, for all x belongs to the real number R, then for all x belongs to capital R and 0 less than or equal to small t less than or equal to capital T, we have, or we need to show that need to show that mod of u1 of xt minus u2 of xt is less than epsilon for any given epsilon greater than 0. So this we need to show for all x belongs to R and 0 less than or equal to t less than or equal to t, we have mod of u1 of xt minus u2 of xt is less than epsilon for a given epsilon greater than 0. Thus we need to find this. Since u1 is the solution of the Cauchy problem with the initial conditions, u1 is the solution of the Cauchy problem with the u at x0 is equal to f1 of x and ut at x0 equal to g of x, sorry, g1 of x by D'Alembert's formula. We have what u at xt, the solution u at xt is equal to, the solution is u1 at xt is equal to f1 of x plus ct plus f1 of x minus ct by 2 plus 1 by 2c integral x minus ct to x plus ct g1 of s ds. Similarly, for u2, we have u2 at xt is equal to f2 of xt, f2 at x plus ct 1 by 2 into f2 of x plus ct plus f2 of x minus ct plus 1 by 2c integral x minus ct to x plus ct g2 of s ds. So this is about the formula for G1 and U1 and the two solutions U1 and U2 of the Cauchy problem 1. And let this be the Cauchy problem. That is, this is 1. Okay. So we have the two formula for D'Alembert's formula for U1 and U2. Now we need to show that for any for all x belong to R and 0 less than or equal to t less than or equal to capital T. For all x belongs to R and 0 less than or equal to t less than or equal to capital T, we have mod of u1 of xt minus u2 of xt is equal to modulus of 1 by 2 into f1 of x plus ct plus f1 of x minus ct plus 1 by 2c integral x minus ct to x plus ct g1 of s ds minus 1 by 2 into f2 of x plus ct plus f2 of x minus ct minus 1 by 2c integral x minus ct to x plus ct g2 of s ds. And under the modulus sign, or this is equal to mod of, now we can combine this with the f1 and f2 like that in order to apply the hypothesis or the assumption. So it is, we can write it as 1 by 2 into f1 of x plus ct minus f2 at x plus ct. And again plus 1 by 2 into f1 at x minus ct minus f2 at x minus ct. Okay, then the next is 1 by 2c integral. We can combine the two integrals. Since the limit are same, we can write it as a single integral x minus ct to x plus ct g1 of s minus g2 of s ds. So this is under the integral side. Now we know that integral of a plus b is less than or equal to, modulus of a plus b less than or equal to modulus a plus mod b. So this is less than or equal to mod of f1 of x plus ct minus f2 at x plus ct by 2 plus f1 of x minus ct minus f2 of x minus ct by 2. is in the modulus sign. Plus modulus of integral will be integral of the less than or equal to integral of the modulus. So this is 1 by 2c integral x minus ct to x plus ct modulus of g1 of s minus g2 of s ds. Okay. Um, Now we know that mode of f1 minus f2 for any values of x and t greater than 0, we have mode f1 minus f2 is less than delta, and similarly the second term also we can write as this is less than delta, and then plus 1 by 2c into mode of g1 minus g2s is also less than delta. Then this will be is less than uh, 1 by 2 into delta plus 1 by 2c into delta into x plus ct minus x minus ct. So this is 2ct. Okay. So 2c and 2c get cancelled. This will be delta. Okay. This is delta plus but this is which is equal to this one, that is, or this is less than this and this is less than. Now we have 0 less than or equal to t less than capital T, less than or equal to capital T. Therefore this is uh, it is delta plus capital T into delta, or 1 plus capital T into delta. So this is less than 1 plus capital T into delta. Okay, so that is we have obtained it as mod of u1 at xt minus u2 at xt is less than 1 plus t into delta. Okay, therefore for a given epsilon greater than 0, we can take delta as epsilon by 1 plus t. Delta is, or a delta is less than epsilon by 1 plus t. So if we choose delta is like this, we have the stability condition. That means according to the small change in the initial conditions, we have seen that the change in the solution is also negligibly small, since it is less than epsilon by 1 plus capital T. Okay. Then for all x belonging to R and 0 less than or equal to t less than or equal to capital T, we have mod of u1 at xt minus u2 at xt is less than epsilon. So this is about the well-posedness. The stability is also we proved. So the problem, the Cauchy problem is well uh, well-posed. Now remark. Number 1. The Cauchy problem is The Cauchy problem is ill-posed on the domain minus infinity less than x less than infinity and d is greater than or equal to 0. So the Cauchy problem will be ill-posed in this domain. And also D'Alembert solution is or formula is also valid for minus infinity less than x less than infinity and capital T is less than small t less than or equal to 0. So the second one is the D'Alembert's formula is also valid for minus infinity less than x less than infinity and capital T less than small t less than or equal to 0. And the Cauchy problem is also well posed in this domain. So the remarks are mainly about the problem. The Cauchy problem is ill-posed on the domain minus infinity less than x less than infinity and t greater than 0. And the second one is the D'Alembert's formula is also valid for minus infinity less than x less than infinity and capital T less than small t which is less than or equal to 0. And the Cauchy problem is also well posed in this domain. So this about the well-posedness of the uh, Cauchy problem of one-dimensional wave equation. Okay, thank you all.